Okay, hello, absent students. So today is going to be 10.7. Oh, wait. Yes, here's a video for 10.7. Honestly, this should go pretty quick. But you might have to stop and then do some work or just like re-listen to some stuff in case you don't get it the first time. But anyways, oh, let me mute my phone. Anyways, 10.7 opener. So this is a quick recap of what we did last class in 10.6, but we are sketching the parametric equations right here. And remember what we did was switching back between rectangular and parametric. And another word for rectangular is Cartesian. But yeah, this is what we did last time. So you're going to make sure your calculator is in parametric mode by going to mode and then changing that from, I actually don't know what it's from, but yes, change that to parametric. And then you're going to plug in your t-step to be pi over 30 and your x equaling to 2 cosine t and your y equals 3 sine t. Okay. One thing you also have to do is because your table here is going in increments of pi over 4, we scroll down a little bit, you can see you're going to want to make your table go in increments of pi over 4, like so. And you would get to this by doing second and window. All right. But yeah, go ahead and graph. If yours looks like a circle, like this, just a regular circle, then that means you need to come or go to zoom and then press 5, which stands for, I think, zoom square. Okay, and then this will give you this oval shape that you see on my screen. But go ahead and pause, plug that in, check it, and make sure it's matching up with this. Cool. All right, jumping into 10.7, we are now looking at polar coordinates. As we just said, we did last class parametric stuff, but today is going to be all polar things. We're also going to do, like in 10.6, see it juxtaposed with rectangular coordinates. So we're going to take rectangular coordinates, and then we're going to flip-flop between those and polar coordinates. So remember, rectangular is just x and y. This is what we've seen all our lives. Polar coordinates, however, are going to be r, which stands for directed distance, comma theta. That's going to be how we find our points in polar coordinates. Okay. So here are 3 examples of polar coordinates and plotting them. So if we look at this first one, we have a 2 in the r spot and pi over 3 in the theta spot. So these concentric circles, right? You see these going around, horrible circles, but right, these circles, right now we have them labeled as just 1 through 3. So we would go 1, 2 to this spot for our r equals 2. And then, right, we're doing unit circle stuff. Where is pi over 3 in our unit circle? It would bring us to this point right here. Cool, not too bad. Same dealio on the second one. This time we are at r equals 3. So we're going to come out to the third most outer ring. And what we have in our theta is a negative pi over 6. So instead of going clockwise, or sorry, instead of going counterclockwise, like we did with our first one, for the negative pi over 6, we will be rotating clockwise. Cool. So this brings us down right here. Very fun. And here, this third example, we can see that even with different coordinates, we may end up in the same spot. So our r is the same. R is 3, so we're again in the outermost circle. But we have a clockwise rotation of 11 pi over 6. However, if you can notice, it brings us right here. And this is equivalent to the second one we graphed, right? The second one, we went the clockwise direction, but this third one, we went all the way around almost and ended at 11 pi over 6. Cool. Nice. All right. So theta, which is the second point of polar coordinates, is the counterclockwise angle from the polar axis. So you always want to measure from the polar axis, which, we can kind of just envision as our x-axis. And we're always going to be wanting to go counterclockwise. This was just an example earlier. But we do always want to go counterclockwise from the polar axis. And now we are looking at four equations that will help us transition from rectangular to polar and from polar to rectangular. Okay, so I am expecting you to memorize these, but it's not too bad. Rectangular to polar, right? We would want to use tangent theta equals y over x. This is going to give us our y and x value. Duh. R squared equals x squared plus y squared. Just remember that. That's simple enough. Polar to rectangular, right? We're going from having an r, having a theta, and trying to figure out what our x and y values are. So, right, x, it's kind of self-explanatory that we would want to deal with cosine. And when we're using y, we would deal with sine. So those are not too bad to memorize. There is a small acronym here. This is like the SOHCAHTOA equivalent, but it's like much worse because SOHCAHTOA is really nice, just rolls off the tongue, but this is horrible, not super helpful as an acronym. But if you want to memorize these random arbitrary letters, you would see that it's sine, like SYR equals sine equals y over r. The CXR would be cosine equals x over r. And lastly, TYX is just tangent equals y over x. Okay, so not the most helpful, but if your brain works well with letters, you can go ahead and memorize that. But let's go ahead and practice a little bit. So we're going to plot the points in polar coordinates that are given here. So A, we have 16, comma 5 pi over 2. So 16 is my r, 5 pi over 2 is my theta. So 16, easy enough, right? I have a lot of circles here, but definitely not enough to go up to 16. So I'm going to just mark these off in increments of 4, right? That'll be very helpful, bringing us to 16 on the fourth one. And then now looking at my theta, I have 5 pi over 2. Just from being a unit circle master, which you guys should all be as well, right? We know that 5 pi over 2 is essentially 2 pi plus pi over 2, right? This is really helpful because this tells me that like that one rotation, not important. All I need to know is that our radian is going to be doing pi over 2. So, right, 16 and then pi over 2, where is that in the unit circle? It is at 90 degrees. So my position for my polar coordinates will be right here. Okay, so 16, 5 pi over 2. Okay, and remember, just to clarify, what we did was we basically went around in one rotation and then ended up here. Okay, 5 pi over 2 is the same as pi over 2 when graphing in polar coordinates. So like another way we could write this that's equivalent to this stuff would be just 16 and pi over 2. Nice. Okay, B, convert to rectangular coordinates. So we're not going to necessarily graph this one, but if I want to go from polar to rectangular, that's what we're doing. So these are polar. We have r and theta. And if you just scroll up, look at your previous slides, right? What am I using for polar to rectangular? I'm going to be using x equals r cosine theta. and y equals r sine theta. Right, plug in my r and my theta. Cool. And when is cosine 7 pi over 6? That is at negative root 3 over 2. And then when is sine 7 pi over 6, that would be at negative 1/2. So you're going to multiply. Don't forget about the negative 2's. You're going to multiply these out to them, this, and then you will end up with an x equaling root 3, and then a y equaling 1. Okay, so you would finalize your coordinates as root 3, 1. Nice. Very good. Let's keep chugging along. Here's some more practice. Let's skip D, but we can do C. Convert to polar. So right now we have rectangular and we're going to polar. So go ahead and look at go a few slides up and see your equations. What are we using? Yes, correct. R squared, oops, R squared equals x squared plus y squared, and tangent theta equals y over x. All right, so plug in your x and y, simple enough. You would end up with r squared equals 18, or r equals 3 root 2. And then tangent, you would plug in negative 3 over negative 3, giving you theta equals inverse tangent of 1. Okay, so I skipped a few steps there, but hopefully you can see what I did. This will give you a theta of pi over 4. Okay, now here's one thing we need to note. Our R here is fine. That's chilling. That's just your directed angle. But our theta, we need to be careful and knowing where we are in our quadrants, because whatever quadrant we're in, right, in this case, the coordinates from earlier put us in what quadrant? Quadrant 3, right? So what this theta is telling us right here is that our quadrant is, or our theta is pi over 4 in the third quadrant. So the reason we have to be careful is that whenever we do polar coordinates, where are we measuring from our theta, right? We're measuring from the polar axis. So it has to come from this line right here and go all the way around. So our pi over 4 being in quadrant 3 means that we need to add a pi so that it brings us around that top half of the unit circle. So our final coordinates would be 3 root 2, that's our R, and pi over 4 plus pi, which is 5 pi over 4. Nice. All right. You guys go ahead and try this. So you can pause the video and take a look while I take a sip of water. Okay, so we are going to convert to rectangular for these polar coordinates, r and theta. So what are our equations, right? Hopefully you're starting to slowly have them get memorized. We have y equals r sine theta, x equals r cosine theta. Plug in our r, plug in our theta. 3 pi over 6, that's just, let's just simplify that, right? That would be pi over 2. Super simple angle for us. We love it. Sine at pi over 2 is 1, so we get 4 times 1, which is 4. Cosine at pi over 2 is 0, and 0 times 4 is 0, so we end up with a coordinate of 0, 4. Okay. Also, just a nice little practice. If you want to practice graphing the polar coordinate, that would bring you right here, right? 1, 2, 3, 4, and then all the way at pi over 2. Next one, a point is given in all right, so a rectangular, X and Y. Sick. And we're gonna transition to polar. So we're going to use r squared equals x squared plus y squared. And tangent theta equals y over x. Plug this in, you get r equals 2 root 2. And tangent theta would become theta over, or theta equals inverse tangent of 1, which is pi over 4. We are in quadrant 1, so we can just leave it as pi over 4, giving us polar coordinates of 2 root 2, comma, pi over 4. And if you want to graph this, let's just say that the second ring is an r of 2 root 2, just to make life easier. But it would be like right here, right? Pi over 4. Right. All right, almost done. Hopefully this is making some sense to you guys. But we're going to practice plugging it in our calculator. So you're just going to go ahead and make sure that you change from parametric, which is what we did at the beginning of class or at the beginning of the video, to polar. And then all you're going to do is plug in r equals 2. Simple enough. Okay. To plug that in, you might have to change your window values and stuff, and make sure you remember zoom squared is very helpful. But you should get a nice little circle here. It's okay if it's a little lumpy. That just means that you want to change like your theta step and stuff. But yeah, let's see really quick a little bit of the relationship like actually pan out. So find the corresponding polar equation. Oh, oops, this should be rectangular. Sorry about that. Rectangular, find the following rectangular equation because we're given a polar part, which is r equals 2. So I'm going to use this one, right? Because we're given r. So like, I mean, these bottom two wouldn't be super helpful, but like tangent's not going to be that helpful either because we don't have our theta. But look at this, x squared plus y squared equals r2. Let's plug in r2, gives us 4. And then if we move this over here, we end up with an equation for our circle. Wow, look at that connection. Yay. Conics. Anyways, keep chugging along. Here we go. More practice. Convert the rectangular equation to polar. Okay, so I know earlier it does say like rectangular to polar, you're using these two. Polar to rectangular, you're using these two. But it's not necessarily saying that you can't use the other equations for other things. It's just saying generally that is what's helpful, is to categorize them in those two categories. But let's look at this, right? We're converting this rectangular one because we have x and y to polar. But what's going to be really helpful for us is actually using r sine theta equal to y and r cosine theta equal to x. Okay, because if you look at this, we have x and y values that are just waiting to be used. So we're just going to plug those in. R sine theta for y, and then r cosine theta for x. And then from here, you're just going to solve, like I can divide by r, which cancels these out. And then let's move cosine to the other side, giving us sine theta over cosine theta equal to 1. And we can even further evaluate by doing tangent theta is equal to 1. Nice. All right, look at B. We have another x here. No y though. So let's just plug in for what we know, which is our x. So r cosine theta is equal to 4a. And I mean, we're converting to polar, right? So I'm just going to isolate this r, giving me r equals 4a over cosine theta. Nice. All right, one of our last problems. Why don't you go ahead and pause to try this one? Okay, so converting this to a rectangular, or converting this rectangular one to polar. Same deal, like I have my X and Y, right? So automatically, whenever I see a variable, I should always be thinking, what can I do with that? So we know we can plug in and substitute X and Y. So I'm going to do 3 times R cosine theta plus 5 times R sine theta minus 2 equals 0. All right. And then what's next? Why don't we isolate to try to find our variables? In this case, we'll be looking for R to make it polar. But I'm going to add 2 over, giving me R, 3R cosine theta plus 5R sine theta equal to 2. And then just a little algebra here. Honestly, the whole day today has been algebra, just manipulating our variables. But I'm going to pull out R. And I'm going to end up with R times 3 cosine theta plus 5 sine theta. Lastly, I'm going to divide by this to isolate R, giving me R equals 2 divided by 3 cosine theta plus 5 sine theta. Beautiful. Great work. Last part. I want you guys to just try plugging this into your, actually wait, hold up, never mind. This is actually the last practice. Yeah. Okay. Don't worry about graphing this one, or like don't worry about this thing. But how would I solve this, right? I'm looking at this and I'm trying to convert it to rectangular. So I'm gonna start plugging in things. Remember these equations, like this looks like it might be helpful, right? Because of this R, but it's not squared, so there's nothing we can do yet. But what do I see here? I see a sine theta. So I'm going to look at this sine equation and see how can I fit that in, right? Maybe since we only have sine theta, why don't I move this R to be under Y so that I can plug in sine and substitute it. So we're going to do R equals 4, and instead of sine theta, right, we're changing it to be Y over R like this, okay? And now, like, we're going to try to substitute for Y or solve for Y because we're trying to make it rectangular. So I'm going to multiply by R, which gives me R squared equals 4Y. And then look at that. We get an R squared, which we know we can plug in X squared plus Y squared equals 4Y. Move this 4Y over, giving you X squared plus Y squared minus 4Y equals 0. Nice. All right, last thing that I want you to try, just practice graphing this. You're going to plug in 2 sine 3 theta. This is not a 30. This is 3 theta. And you should get this shape. It's like kind of looks like a flower. Or like the petals of a flower. But yeah, if it's not looking very nice, then just make sure you go to zoom and then 5 zoom square. All right, cool. That's the end. If you want extra practice, right, you can convert this to polar and, oh, sorry, convert from this polar equation to rectangular. And all the steps are here for you to double check. But for all my other classes, we kind of just, or all the in-person classes, we kind of just stopped here. But good job, everyone. We'll call it a day. Hope to see you in class soon. Goodbye.